Let me first join everybody in thanking the organizers for inviting me. And I'm looking forward to the discussion for the week. It's a very interesting crowd for me. One apology, one let's say, disclaimer. I have a little bit of a cold, so I may faint at the middle of the seminar, but I hope the voice will survive. Anyway, okay. So I wanted to do a full seminar about electrodynamics, about the cavity electrodynamic, but then given the topic of the meeting that you have here, which is like the use of quantum optics for condensed matter, or the use of quantum optics technique for condensed matter, I thought of inserting a few other parts just to show a bit the logic of what we're doing. There's no need to introduce this topic to this community. What I particularly like of Dimitri's summary is this slide that they made, because there's like all the keywords that people used in the community, from nonlinear phononics to the concept of metastability and Floquet, and eventually also the use of topology. Of course, everybody choose the tools that they want, and the tool I will use to explain what's the logic that drives us is the tool of nonlinear phononics, and I will explain you. I will try to convey the message of what's our choice and how did we get to cavity electrodynamics, and I'll bring forward some discussion there. So I'll start from an experiment that we published a few years ago. The experiment is not very relevant here, but what I want to use it for, I want to use it to give a little bit of the idea of what is the philosophy that we're trying to follow. So in this experiment, we wanted to demonstrate that we can use a vibrational driving of a system to control electronic excitation. So we choose a system where the electronic excitations are not visible, or they should not be visible in linear response, but yet they are visible, and they are discussed in literature. There's a fairly long literature discussing them as phonon-assisted transition. So for us, this was just the ideal platform to demonstrate that if I drive vibrational modes, I can gate electronic transition so that I can demonstrate that effectively this nonlinear phononic works. And I will use this to explain what the kind of experiment that we do. This is the experiment that you will hear also from other speakers during the week. The idea is the idea that we want to resonantly drive some vibrational excitation and look at how these vibrational excitations affect the electronic properties of a system. And the important result that I think is the message that I want you to take away is the following, that in this case, as in many others, what happens when I drive the system with a coherent excitation is very different than what happens when I just turn on the temperature. In this specific case, if I increase the temperature, this electronic excitation becomes more absorptive, while what we observe with a resonant drive of infrared mode, it's actually a region of transparency, which is very much at odds with thermodynamic situation. How do people reason about it? Well, people reason about it introducing the concept of nonlinear phononics, where essentially by driving some vibrational mode, I can actually lead to the displacement of some Raman mode along some other coordinate, and this is like the idea where if I drive the system strongly along one of the eigenmode, which is dipole active, I can lead the system to produce some displacement along other directions which may be relevant for thermodynamics. And people describe this idea very much in analogy with a similar coupling term, which is of the kind Q square, where I basically, by driving a dipole excitation, I change the amount of excitations or the amount of fluctuations I introduce into the system into the relevant degrees of freedom. And the point here, I want to make 2 points with these slides. The first point is relative to nonlinear phononics, in the sense that the two terms where I couple linearly and where I couple quadratically, they are often described in the same way, but they do something very different, because while the linear coupling produces a displacement on the arrival mode, the quadratic coupling produce instead fluctuations on the arrival mode. So that we should think about it in a very different term, in my opinion. And the second message that I want to give relates to the fact as we have seen nicely in June's seminar, that what happens with nonlinear photonics is that we couple to certain degrees of freedom, but the relevant thermodynamics is somewhere else in the system. It's on other degrees of freedom which are affected by my drive. I do not control directly the drive. And whenever we will do the cavity electrodynamics, this is the same philosophy that we will follow, because we are not searching, we will not search for a transition, phase transition directly to the mode that we couple to the cavity, but we are searching for the consequence that this coupling have on the rest of the thermodynamics of the system. Okay, so that's the difference in approach. So we will not be looking much for a strong coupling, but we will looking at the thermodynamic consequences that even weak coupling can have. Okay, and I'm also happy to take questions, so just stop me. Okay. So these first minutes were essentially to highlight the philosophy that, in my opinion, whenever we want to try to control thermodynamics in complex material, we need to try to access fluctuations, which comes either from nonlinear coupling or from engineering the electromagnetic environment, as I will try to discuss in the following. So the activity that we did was along the line of, after realizing that fluctuations are the key parameters, we're along the line of trying to understand what can I do to measure fluctuations. And this is like very much at the core of the topic of the meeting at the ITP, because we resort to quantum optics techniques. So we basically used a lot, developed a lot of fluctuation measurement for the light, so that having in mind what do I learn about the fluctuations in matter in these systems. And the second part of the seminar will be about controlling fluctuations, and there I will connect with cavity electrodynamics, even though, as I said, we are not really searching for strong coupling regime, but we are actually trying to control radiative coupling through cavity electrodynamics. And I will try to draw some perspective at the end. So what did we do with fluctuations? There's a lot I could show, and I tried to find like a summary of what we did in the past, just to show a little bit what's the main ideas, and also some new results that we have. So how do we measure? How do we use quantum optics to measure fluctuations in matter? And the idea, it's fairly simple. So whenever you do a time domain experiment, you use light on one hand as a perturbation to inject some dynamics, and a second light pulse to measure this dynamical response. And usually, if you measure mean value response, like you say, I measure, for instance, how the reflectivity of an object evolves, how the transmittivity of an object evolves, what do I do from the light point of view? I actually measure expectation value of operators, which is just, I have a mean photon number in, mean photon number out, and that's all the information that I acquire. But if I look at the problem from the point of view of light, of what happens to the probe light, obviously I can store much more information into this probe. I can, for instance, ask myself, what is the spectroscopic information which I have in photon number fluctuations? Do photon number fluctuations, so I apologize for my English, but it's also part of the code. So do photon number fluctuations carry a spectroscopic information which is not there if I just measure mean values? And in this sense, we did a lot, and we got convinced that in relatively clean systems where the Hamiltonian process is very much under control, we can map certain kind of atomic fluctuations or fluctuations of the atomic positions into photonic observables. And I'll just spend a couple of slides to highlight the recent effort in this direction. This is an idea of former students of mine who came up with an idea. We were doing a lot of tomography at that time, where we would reconstruct the state of the light just to measure a few light pulses with only a few photons. And he came up with the idea saying, but what happens if we actually do benefits of the heterodyne techniques without having to pay in the price that I need phase stability, which is always a problem in experiments. And he came up with a very strange experiment where he said, okay, but if I take an OPA and I tune the OPA so that the signal frequency is twice the signal of the idler, and then I frequency double the idler, And I said, okay, I will do a degenerate pump and probe, which is exactly the same that I could do by splitting this local oscillator. And she said, yes, but if you think about this problem from the point of view of the phases of the field, when you do this, you can actually have a random phase relationship between the probe pulses and the signal pulses. So if I heterodyne a pulse which has only a few photons per pulse with a local oscillator which comes from the signal, the phase relationship will be random. And that actually bypasses completely the problem of phase instability and makes the system very much controllable. So, sorry? I tune it. I tune it such that the Heidler helps. So the sum of the frequency of signal and Heidler should be the frequency of the laser, and I tune the Heidler such that it has half the frequency of the signal. Just a very naive tuning of the OPA where I just select.
The OPA is not seeded, so you don't.
The OPA is always seeded by the laser, so it inherits the phase of the laser.
But it's not seeded by a white light.
It's seeded by a white light, therefore the fluctuations that we will have will be like the fluctuations which I have in the laser fields, which I don't control. But let me just show the evidence. Okay. Yeah, it will become clear. So it's an idea which at surface it looks weird, but then you just dig into this and you say, okay, let's see what kind of observable should I have. Well, if I measure the quadrature of a phase which has a random phase, I will actually acquire a distribution on the phases which is completely random. So whenever I acquire the histogram of my data, I expect to measure quadrature distributions which are like this. And you can resort to quantum optics, as I wanted to connect to the topic of the meeting at KITP. You can resort to quantum optics and you can demonstrate that if the phase is distributed randomly or decently randomly, you can use this information to retrieve all you can do a maximal likelihood tomography, which allows you to reconstruct the photon number probability even with few photon states. Okay, so it's fairly simple. So you just say, I throw away all of diagonal terms and I have enough information to acquire all the distributions. Yes? Yes?
Sorry for the naive question, but isn't that exactly the setup people do for doing squeezing? You do a parametric generation seeded by vacuum, and then you frequency double and you interfere.
Yeah.
So you should basically see squeezing on your...
Yeah, but if you don't control the relative phase between the two, then overall the phase is random. This we tested, at least.
Okay, yes, sure.
Yes. So, but this is like, so these are like very intense pulses. So this is like a seeded optical parametric amplifications, which is in the saturation regime as we build our OPAs for using them as pumps. Yes. So, yeah, this is well into the saturation regime of the OPAs.
Excuse me, but if the phase is random, what is it measuring then?
The phase is random. I measure the heterodyne. I measure the heterodyne.
But now if the phase is random, then I just get, it's like a homodyne that the local oscillator is not a good local oscillator.
The local oscillator will sample random phase. So the relative phase between the local oscillator and the signal is random, and this is the histogram of the measurements that you have. It's simply like saying that if I double the frequency of a signal which inherits the characteristic phase of my laser, I double it up and I have a random phase relationship between the two. But yeah, so yes?
Very naive question. Like
it's classical phase anyway.
Like what happens if you start from like the standard homodyne and then add a random phase shifter to one of the arms?
Sorry,
like is there anything special?
What happens
if you start from the standard like homodyne or heterodyne, like where you go like use the same optical setup but without the OPA, and then you add a random phase shifter in one of the arms? Like I guess I'm just confused.
You could do it. Yes. You could add a random phase shift between the two. Yes.
So the OPA is just like
a smart way of doing it, yes. Because you use the fluctuations of the laser. It's just very simple. So the idea is that, maybe one question on this and then. I would like to not take over too much time. Yes?
On the same topic, couldn't you just extend one of the arms of the interferometer beyond the coherence length?
Yeah, but that's a laser. These are very intense laser pulses, which are produced well in the saturation regime of the OPAs, so I wouldn't, yeah, it would probably extend the interferometer a lot anyway. It would be much, yeah, it would be unreasonable, I think. But anyway, but the point is that you can do a maximal likelihood. You don't have much information, but you have information on all the photon number, all the diagonal element of the density matrix of the photonic states. Okay. You can actually obviously change the intensity of the states, and you can measure the full distribution of the atomic state. Oh, sorry, the full distribution of the full photon number distributions. And the interesting thing is that the technique is easy enough so that now I can add a pump to the problem, and I can measure the distribution of the photon number as a function of time, and you see the characteristic signal of a phononic mode. And what I find interesting is the fact that now I can measure the full distribution, and I still have features which are associated to the phonon oscillations, which are actually, which I can measure with very few photons per pulse. So this is like adding a pump. This is a phonon mode it was in the previous slide on quartz.
Quartz.
Yes. So you get out funny numbers, like for instance, you can measure how the probability of having any given photon evolve in time, and you can even have the time evolution of the probability of having no photons in your probe pulse if you have a weak state. But essentially, what we came to realize is that we can put boundaries if we trust the connection which I have. I have fully under control the optical problem, and I have to define an Hamiltonian interaction to couple the light to the phonons, and I can put limits to the non-classicality of the phonon modes. And essentially, in these settings, the result is that whatever we observe, it's still Poisson distribution, and there's no non-classicality of the phonon mode. But it's just like to connect to how can you use quantum optics to address condensed matter problems. So we did a lot in this sense, and we also did a lot using classical fluctuations of light. And I just also want to give you one result that we are working on that I will connect at the end when I will go back to the cavity. So the idea, this I give it I will not explain, but we develop means to produce very phase randomized states where basically I introduce fluctuations in my light pulses, which is uncorrelated in frequency. And what we developed in the past over a few years and in different papers, this is the starting paper, but there's been a few others, we developed the means to produce random fluctuations in the phase. And if you take the same set of pulses and you make them interact with a sample, and you look at them one by one, obviously you don't learn much, but if you look at the correlations, you get out the phonon of the sample that you put in interaction with the light. So essentially, it's a good mean that you have to extract the frequency of the boson which mediate the correlations that you introduce in light. So this is like we did it on simple system for a while, and what we did recently, and here I will ask you again another loop of faith. I just dropped the results. So we asked ourselves whether we can have signatures which are associated to scattering process from superconducting fluctuations in this manner, and we resort to Raman spectroscopy, and there's a long list of publications in starting or actually ending with this review of Tom, on what are the kind of information that you get out from electronic Raman scattering in superconductors. And there's like, in high temperature superconductors, there's a very broad scattering feature, which is associated to the presence of a superconducting gap. And we did our noise correlation analysis. I spare you the detail, but what it turns out is that we can observe an electronic Raman scattering which is suggestively similar to the electronic Raman scattering that it's observed with static Raman spectroscopy. Mind you, this is a different observable, but it is somewhat associated to the presence of superconductivity in the system. How do we convince ourselves that we do have evidence of this broadband electronic Raman scattering? Well, first of all, we studied the dynamics, and the dynamics of this scattering is consistent with the dynamics I know from many other observables of the superconducting state. But more than anything, I try to look at this electronic Raman scattering in the normal phase, and I have no electronic Raman scattering. I look at the electronic Raman scattering in the superconducting phase, and I see features which are similar to the equilibrium Raman in the system. And what was a bit surprise for us was the fact that we could observe features associated to this inelastic scattering throughout the pseudo-gap phase. And this we connected, it's still work in progress, but we connected to the idea that if I probe the system on a short time scale, and the difference between the equilibrium Raman spectroscopy, where in the pseudo-gap phase there's no features associated to electronic Raman scattering, if I study the system on a short time scale with my snapshot interaction, I do see an inelastic scattering feature which is similar to the scattering features I have in the superconducting state. It's work in progress, so we cannot make a statement, but this is like, it could be a way to measure evidence of superconducting fluctuations throughout the pseudo-gap state. So essentially, with a time-integrated probe, I have no evidence of any electronic gap, but if I take a snapshot of the interaction, I do see a scattering feature which looks suspiciously similar to the scattering features I have in the superconducting state. This is just to say, yes, to say the kind of approaches that we have taken to use multimode correlations in light and photon number fluctuations to address condensed matter problem. Yes, one question.
The fluctuations of two fields, or the amplitudes of them, or
what we measure at the end? What we measure at the end is the correlation between the amplitudes. But yeah,
so you do one Raman, and then you do another Raman, and then you look at the correlation between the two output Ramans?
Yes, yes.
With the time difference
yeah, it would be like 8-body correlator. So you measure correlation between intensity rather than photon number scattered in Raman. Yes.
And you filter in frequency. So there is one Raman with
That's the cool thing of the technique, that if you have a broadband pulse, which is very short in time, and you introduce noise, which is narrow in frequency, the overall time resolution, which mixes one photon from the noise and one photon from the broadband pulse, is the time resolution of the broadband pulse. So you have the frequency resolution of the correlation, the bandwidth of the noise, and the time resolution, which is the inverse of the bandwidth of the laser. It's a little bit like femtosecond Raman spectroscopy, but measured in the correlations. Yeah. But I'll be happy to discuss. This is now going to discuss over the week. I'm happy to discuss this, but I wanted to, as I took questions, I also take the full 45 minutes. Yeah. Yeah. So this is just like, I mean, we did a lot to try to use light and statistics of light to understand condensed matter problems, and that's this was just some of the ideas that we were pursuing, that we are pursuing still. On the other hand, obviously, there's like, as I showed in the beginning, there's a big step between, let's say, that the key for controlling thermodynamics is the control of fluctuations, and in this sense, we resort to cavity electrodynamics to control fluctuations. I'm glad that I don't have to introduce anything about cavity electrodynamics, because June did a fantastic job in that. So the only difference is that we were not focusing on rich and strong coupling regime. We did on some of the systems, but more than anything, we are interested in trying to use the cavity to shape the radiative load that I have on the sample, and I'll try to show you what we did. He mentioned that one of the good things would be to have tunability, and we developed our own system to have tunable Fabry-Perot cavities in cryogenic environment, but that's technical details. So what we did, and that's reported in a paper which is from last year. So we studied a system which has a metal insulator transition. So we studied 1T tantalum disulfide, which is characterized by having a charge density wave transition, a charge density wave order, which transit from insulating at low temperature and metallic at high temperature, which is associated to the charge density wave having a periodicity which matches the periodicity of the lattice in the dielectric phase, and instead a disordered charge density wave system above Tc. I will not discuss the physics of this object too much, but essentially it's a system which has a metal insulator transition, which is associated not to the single particle properties of the electron, but to macroscopic transport of charge density waves. We have an observable to measure this phase transition, so this is the terahertz transmittivity as a function of at two different temperatures in the dielectric phase and in the metallic phase. And in the dielectric phase, you have very sharp resonances associated to phonons, which are screened in the metallic phase by the presence of free charges. And this is just to demonstrate that these phonons are a good observable to define the effective phase transition at which I observed the metal insulator transition. So I have a metallic state above Tc and an insulating phase below Tc. And the main observation, I will again just highlight the results. The main observation is that the effective phase transition temperature at which we observe the phase transition is shifted by the presence of the cavity by nearly 50 degrees. So I can actually transit from metallic state to insulating state, and from insulating state to metallic, and I see that effectively the effective temperature at which I observe the phase transition, it's shifted with respect to the system outside of the cavity. The shift is so large that I could use this, at that point, the cavity electrodynamics to control the phase of the material, and this is what we did. So we first studied how these hystereses evolve with photonic parameters, such as the cavity alignment, and we see that by misaligning the cavity, I go from the renormalized hysteresis to the hysteresis I observe outside of the cavity. But what's quite striking is that now I can fix the temperature of the system, meaning I fix the temperature of the support of the sample, and at the same temperature, I set the mirrors. And by tuning the angle of the mirror, I can switch from an insulating behavior to a metallic behavior. And even to the point that I can, by tuning the cavity frequency, I can switch the system from metallic to insulator, and vice versa, from insulator to metallic. So I can fully control the phase transition by playing with photonic parameters associated to the cavity shape and quality factor.
So how large is the translation of the mirrors to tune these modes now? How much do the mirrors
in this specific,
yeah.
you can do the calculation, 50 gigahertz, 11 gigahertz, so the 11 gigahertz is about millimeters, and 50 gigahertz is about sub-millimeters, but not small. But then we did other studies where we went to sub.
You move the mirror by how much to change to drive the metal insulator transition, the flat mirrors?
You can do the calculation.
Well,
50 gigahertz and 11 gigahertz. I would say from 8 millimeter to 1 millimeter. This is just a number, but it's in these slides. Yes. Yes.
So, and what was the frequency of this polariton? So is it, is there the cavity
That is what
resonance?
let me just get to that point. So in this case, we don't know so we did study the coupling to the phonons with high frequency cavities, but the coupling to the phonons where we reach strong coupling, which I will not discuss now, didn't give any thermodynamic effect. The thermodynamic effects were dominated by cavity which are way below the phonons, so which are associated to the coupling to domain fluctuations in the charge density wave systems. But I will discuss this later. So how do we were lucky enough that we didn't have a theory for this experiment, so we could discuss it. And we proposed two different frameworks in which we could discuss together with our theory collaborations, obviously. And you can think about changing the thermodynamic of a material, thinking about the thermodynamics of the material in the free space. What do I mean? By that, I mean that if I do have a phase transition by tuning temperature, it actually means that this is just a sketch to represent this process, that if I am in the insulating phase below a certain critical temperature, then the free energy of the metallic phase becomes favorable above the critical temperature, and therefore I have a phase transition at a given critical temperature. You can think about the cavity as to an object which dresses one of the two phases and not the other, and therefore it changes the free energy of one of the two phases with respect to the other, and this would actually correspond to, if I can change the free energy of a significant amount, I would observe a shift in the observed phase transition that I have in the system. On the other hand, you can also think, so this is like describing the system from the point of view of the thermodynamics. On the other hand, and this is a collaboration with a few people in the crowd, we also, there's a different way in which you can describe this kind of process. There's a more general process in which you can think about an object which is thermodynamically coupled to a photon buff as to an object which is subject to certain radiative heat load, which comes from the photon buff. And what the cavity does, the cavity shapes how does the object sees the photon buff in which it is immersed. So in a sense, whenever you define like the Stefan Boltzmann law, where you have a certain sigma, a certain emissivity, in this emissivity, you have dipole allowed transition in the material, convoluted with the density of states of the photons, of the photon buff with which this material exchange photons. And by shaping the cavity, I can shape this part, and I can shape the emissivity of a material. And we think that this is like effectively what's the dominant factor in the observations that we have, which is the fact that if I do have an open system, I can have a thermodynamic cost which is associated to the fact that the cavity changed the nature of the photonic buff. Okay, so if you think about effects such as like the Parcel effect, usually the Parcel effect, you think at how an electromagnetic environment can change dissipative rays. On the other hand, this change of dissipative rays will have thermodynamic consequences if the system is not just a single atom. And I think that this is, in some sense, it explains the choice that we made, that just to say a very broad statement, I can reach strong coupling when the system is closed, but if the system is closed, it perceives the photon buff in which it is immersed only mildly. On the other hand, if the system is fully open, obviously there's no cavity, but this idea that I can change the radiative heat load doesn't necessarily mean that I will have the largest changes where I have the strongest coupling, okay? Because I need to be able to see the photon buff with which the sample is exchanging energy, essentially, okay? And what I think is a very powerful perspective is that this, in some sense, that's at least where we are setting our research. We're setting our research in the idea that cavity electrodynamics may be the means to bring back at the stationary state whatever we learn from non-equilibriums. And I'll try to just spend the last 2 minutes just, yeah? Yeah, okay. Yeah. So, and that's just to make, I was very surprised, like when 2 weeks ago, there was a paper. suggesting that many effects seen in polariatomic chemistry may be related actually to something similar, to also the fact that the environment, the cavity can change the radiative coupling to the environment. So what I think it's a very nice setting for our research is the following, that we are used to think in physical chemistry about controlling material, and here I connect to Dimitri's first slide to all the techniques that we have. So that we are used to changing physical parameters such as composition, magnetic field, or pressure, but we should think about the electromagnetic environment of an object also as a physical parameter which can affect the thermodynamic of a system. But the difference between the red axis and all the others is that in the red axis, I obviously can have driven systems, and we did a lot on phonon pump, a lot on photodoping, and there are an emerging research direction where people try to use strange state of light to induce dynamics, and that's, I think it's very interesting. But on the other hand, I can use this axis also without the drive that I put artificially, and I can use natural drives like June did in the previous seminar, like using vacuum fluctuations as coupling, or even in what we think is very relevant is thermal buff in the material, in the environment. And this is one specific problem that we will try to tackle. So if I convinced you that there's a lot of literature about the existence of superconducting fluctuation throughout the pseudo-gap phase, we are looking in the future for finding the right cavity setting to mediate long-range interaction between the superconducting fluctuations. Obviously, it's us and other groups which are trying to find the best configuration for doing this. But this is the specificity of the direction that we will do. We will actually develop means to address the thermodynamics, because if I said that it may be possible by changing or by controlling the radiative coupling to an environment to sustain non-equilibrium stationary states, I may be able to measure it if I measure the thermodynamics of all the degrees of freedom. So we will develop means to measure the thermodynamics of the different excitations in the matter, like in time-resolved Raman. And the other effort, which I think it would be like a nice discussion, would be an effort where we try to engineer light-matter coupling, in a sense, giving momentum to the photon, just through this plasmonic structure, as we have seen also in the previous seminar, and I'm sure we will see more in the week, that using plasmonic structure, we can bring the coupling between matter and light, which usually is at zero momentum, we can bring it to finite Q. So at that point, we could treat light as we treat any other boson in condensed matter, such as electron-phonon coupling, or the coupling to any other boson in the system which has momentum. So this is the thing. This is what we're doing ourselves, just both developing the next phase of complex tunable cavity, as well as developing, let's say, very tiny cavities which we can bring around, and they are designed to be smart, to be, let's say, self-compensating. And these are the kind of questions that we want to address. But I think that sustain at the stationary state, non-equilibrium states, it's something which sounds very, very fancy, like a non-equilibrium stationary state, but it's something that nature does regularly. So we have many examples in nature where we have stationary states which are non-equilibrium states. If we can engineer light-matter interactions such that we obtain stationary non-equilibrium states, I think we can do a lot. We can violate fluctuation-dissipation relations, and we can obtain functionalities which we don't have at equilibrium. I think this is why it's very interesting to be in this field. And 30 seconds to thank the crucial people for the cavity has been Giacomo and Shala, and for the mid-infrared pump, Angela, Enrico, and Nitesh. And the theory is done by that's theory support from inside the group, and many other people which collaborated to the different projects I showed. And thank you for your attention. for 45 minutes with the question inside of the seminar.
No, it's perfect. And since you started a little bit late, we have 5 minutes for more questions. Let's see, John.
Thanks. Very interesting. So, is there a sense that you have on it? Let's say this is basically heating preferentially, by focusing thermal fluctuations to the cavity into the degrees of freedom of the system. So, are you heating? So, two questions: are you heating, let's say, in like a low pass sense, like just low energy degrees of freedom, or is it targeting a specific degree of freedom? And also, if I can heat, can I cool? Just like cool the mirrors and heat the sample and reverse the flow of energy?
Yeah, I think in principle you can do it in the sense that what you shape, you have the freedom of shaping your material, and you have the freedom of shaping the number of states that you have in your photonic state, which exchange energy with this material. So we have shown with Martin and Jerome the leading terms will be in the mid-infrared for a photon buff at 300 Kelvin. That's obviously as the emissivity of an object is dominated by the spectral response of this object in this frequency range. But if you shape the cavity, you can both do filtering as well as tuning of the excitation at the proper energy region. And I'm very happy that the polaritonic chemistry community start resonating with these ideas, because this is just a heuristic observation, but most of the polaritonic effects that people reported, they reported polaritonic effects which are resonant to phonon modes, which are in the mid-infrared range, where we know it's the dominant effect. This radiative coupling is the dominant effect.
Yes, there was a question.
Maybe just a quick clarifying question, like this point about using the photonic radiative degrees of freedom as the best, and maybe I just get confused, like if you have an optical cavity, don't you always expect the thermal excitation to be negligible? Wouldn't that always serve as a cooling pass? Maybe I'm just confused, when you write 300 Kelvin radiative pass, what exactly?
You can show that it can work both ways. So if you tune your resonance, so it needs to be thought, but if you tune no, it's not the graph I wanted, but if you tune your resonance on the maximum efficiency of the photon buff, you can have a larger effect that you would have without the cavity.
So can I ask, what is the range of the photonic resonance? Is it?
For a buff at 300 Kelvin, this is 10 micron, 20 micron. It's the range of mid-infrared excitations. But that can be shaped.
In terms of frequency, how does that compare to 300 Kelvin, which is 600 gigahertz, 0.6 terahertz?
That's the phonon 300 Kelvin, yes.
Okay.
20 micron, 10 micron is that number.
Great talk, Daniele. So what prevents you from doing microwave spectroscopy inside the cavity to see exactly what you're doing in the gigahertz range?
Yes, so microwave spectroscopy in terms of the proximity effect, like this Corbino, you cannot go in with the probes because there's always the dielectric mirror in between. So the far microwave is not possible, no. There were techniques to do this, like backwards wave oscillators, but they work at single frequencies, so you cannot do the spectroscopy. And we've tried to set up some program like that, but we couldn't do anything here.
Sebastian.
Very interesting, this prospect of getting this driven stationary state. So, these phase transitions that you have there, do they break also continuous symmetries, or is it just like easing type discrete symmetries? Because in the case of the continuous one, you would probably expect that, this non-equilibrium perturbation can really blow up and give you something genuinely new.
That's a question for you. Yes.
Long way. So any continuous symmetries involved? Or?
That's a question for the theorist.
Maybe in these superconductors it looks like that, yes?
Yes, they are definitely on the scope. Mm-hmm. But the general question should be asked to theorists. Maybe the theorists want to answer.
I have a different question. In the mapping of your quadrature histogram on the random phase experiment, how stable is that with respect to other experimental noise and errors?
That's the real advantage, that this is like, if you don't need phase stability for this, because if you add a stochastic fluctuation of the phase to a phase which is already stochastic, nothing happens. That's the beauty of it, that you can have the benefits of heterodyning without paying the price of heterodyning.
Okay, maybe one final question by Anshul.
Thanks. So I have a couple questions which are related. So if you tune the frequency of the cavity in the tantalum disulfide experiment, do you eventually go to a regime where it starts to go back? Like, are you hitting a resonance, or is it just one way only?
So the way I tell you, the way we argued, so we measure without the mirrors, and that's for us, it's zero frequency. Okay. And then we measure with the largest frequency which we can have, and that's below the zero frequency. And then by tuning it, it goes above. So the logic of our discussion is that there is a resonance below our frequency.
Okay, got you. So
which could be centimeter or meters. So
and it's difficult to. It sounds like one could perform free space microwave spectroscopy, like Eduardo was saying, and perhaps see a mode down there.
Yeah, this was the.
Okay, let's thank Daniele and June and all the other speakers for coming.